Here are a list of keywords discussed in Week 2 for Lecture 4 and Lecture 5. These are excellent terms to put on your flashcards. Hi everyone, so today we're going to cover some of the public land survey system mapping and coordinates that are a little confusing, so hopefully we'll clear up some of that confusion. So from your baseline, anything north and south of your baseline is considered your township. So if you go 2 units from your baseline north or south, you're establishing your township. And the principal meridian is running north and south, so anything east or west of that principal meridian would be your range. So generally your steps for finding a location are as follows. You establish where your township is, your range, your section, and then you go into quarters. Let's suppose you have a question asking what map unit is in the southwest 1/4 of the northwest 1/4 of the southeast 1/4 of section 20 of range 4 east and township 2 north. First, let's start with the township and range to find our section. So here, let's say this is our township 2 north and our range 4 east, and it's mentioned section 20. So here they align in a raster fashion starting from the top right corner. You have 36 sections total, and here we found our section 20. Now that we found our section, let's zoom in a little closer to that section and find our next quarter. Within this section, we are looking for the southeast 1/4 as shown in the diagram. To find our next quarter, we need to zoom into this area and quarter it again. Here is a diagram of the southeast 1/4 of section 20, where we now need to find the northwest 1/4. Now we will quarter it one more time to find our southwest 1/4.
Chapter 8 in your textbook goes over soil colloids. So read chapter 8, and we're going to talk about the elemental shapes of soil colloids. So first is the tetrahedral, meaning it has four sides or 4 faces. So in the middle we have the silicon element, and it's surrounded by 4 oxygens. So here is a tetrahedral sheet where we have tetrahedrals bound to other tetrahedrals. So since all the oxygens are bound up, they each exhibit a -1 charge. So 4 negative charges of the oxygen plus the +4 from the silicon gives a no net charge in the tetrahedral sheet. And then another thing to note is the different oxygens within the tetrahedrals have different names. So the basal oxygens are the oxygens in the tetrahedral sheet that's bound to other tetrahedrals. The apical oxygens are oxygens that's bound to another sheet, like an octahedral sheet. Next, we're going to talk about the octahedral shape. So the octahedral has 8 faces or 8 sides, and in the middle we have an aluminum element surrounded by 6 oxygens. And then the octahedrals bound to other octahedrals make up an octahedral sheet that also has a no net charge. Something to note is isomorphic substitution. Isomorphic substitution happens when an element of similar radius size bumps out your original element.
Just for clarification, when we say bump out, we don't mean that the element is exchangeable, but rather that when the mineral is forming, a different element of similar radius size is fixed into the structure.
So let's, for example, say aluminum, which has the same radius size as silica, and it will bump out the silica. But that changes the charge because aluminum is a +3 when silica originally was a +4. So that changes your tetrahedral sheet, which originally had a no net charge, and now you change a +4 to a +3, you now have a -1 charge. So let's look at another example. Let's go to the octahedral sheet, which has the aluminum +3 charge. So we're going to put in an isomorphic substitution, a similar radius element like iron 2+. So iron 2+ with a similar radius will bump out aluminum 3+. So the 3+ then becomes a 2+. So the octahedral sheet, instead of having a no net charge, will then have a -1 charge.
Another topic that was discussed this week was the difference between permanent charge and pH-dependent charge. So like we discussed earlier, isomorphic substitution changes the permanent charge on a mineral structure, where pH-dependent charge is dependent on the pH of the environment. So having more hydrogen protons on the exterior of the soil mineral surface is going to change the charge, so it is pH-dependent. Permanent charge does not, the environment does not influence its charge. Alright, so we talked about the different layers that you can get from tetrahedrals and octahedrals, but why does that matter to clay mineralogy? It's because the assortment of the tetrahedral to octahedral sheets give us some distinct features of our clay minerals. So here we have a 2-to-1 tet to oct layer where you have a tetrahedral sheet, an octahedral sheet, and then a tetrahedral sheet. These sheets will combine with other sheets, giving you this distinct tet-octet over a tet-octet. And here, this is the inner layer space between these two sheets. Additionally, you can have a ratio of 1-to-1 of tetrahedral sheets and octahedral sheets, or you can have something similar to this. Here you have an inner layer space, and here you do not. In class, we visualize this using Oreo cookies. So the top part of your Oreo cookie is your tetrahedral sheet. The filling is the octahedral sheet, and the bottom part is the tetrahedral sheet. So when you look at clay minerals, you don't necessarily just look at one sheet or one cookie, you look at an assortment of cookies, and how these space between each other give you an idea of what clay is present.